Hello world, my name is Victor Engelmann, and in this video I'm going to explain assembler to you. In my channel I've mentioned assembler here and there, and as a scientist it feels kind of dirty to talk about something without defining it first. So I want to fill that gap and explain assembler here. There are pretty good assembler tutorials on YouTube already, so since I see my channel kind of as the resource where you get the information that you get nowhere else because they are too complicated, I don't want to go too deep into this topic, so I'm gonna limit myself to a crash course in assembler here. Okay, what is assembler? You could call it a programming language, but that depends a bit on how you define the term programming language. Because if you think about high-level programming languages with control structures like functions and loops and branching, you don't have that in assembler. In assembler, you program the processor directly, so you tell the processor exactly what to do. And if you want to have some high-level behavior, you have to map that in a way, and you have to find some ways to mimic that behavior in assembler. So let's say this is your processor, and here's your RAM. Okay. The CPU has some so-called registers, which is some additional memory. And for example, you have a register called A, a register called B. And that's some additional memory where you can put some data in. And for example, you can take some constant number like 0 and move it to RAX, which means that you write the number 0 into this register. Okay, and constant numbers are prefixed with this $sign, and registers are prefixed with a %. And in 64-bit programming, they start with an R, and they typically end with an X. That's for historic reasons. I don't want to go into that. That's one thing that you can do in assembler. You can put some number into a register, or you could take the content of one register and copy it to another register, RBX for example. Okay, or you could say add two numbers by saying %RBX add to %RAX, then A will get the sum of A and B. Okay, this is really low-level stuff, and it's kind of hard programming with that. But when you're writing a compiler, for example, you need to know at least some assembler, because this is what you are in the end generating, right? And an assembler program starts at some point and then goes down and just executes one of these instructions after the other. Okay? And as I said, there aren't so many of these instructions. By the way, I should mention that I'm using the GNU Assembler syntax here. There are different assemblers. NetWide assembler, GASM is quite popular. But that has a very different syntax. There the operands would be swapped. I I think the GNU syntax just makes sense. You know, you're reading from left to right, and yeah, these instructions, when you think about them reading from left to right, you start here, then you take one of the operands, the first operand, and apply it to the next operand, right? So move 0 RAX means that you put 0 into RAX. And I think that makes sense when you think about it like that. But yeah, as I said, most other assemblers have this the other way around, but yeah. I prefer GNU Assembler because it's GNU, and yeah, that's what I'm using here. Another, by the way, since GNU Assembler is not really the most popular assembler, if you Google anything about assembler, you will typically find results for NetWide Assembler or other assemblers. And if you want results for GNU Assembler, you should always add GNU GASM to your search terms. Okay, so otherwise you will typically not find stuff about the GNU Assembler. So yeah, you can also copy data from the registers into the memory. You can copy data from memory into the registers, and you can do some calculations, but only with data inside the registers typically. So so yeah, that's really very limited. If you think about evaluating a term like 3 plus 2 times 4 or something, yeah, the assembler doesn't allow you to do that directly, you know, unlike high-level programming languages. So if you want to calculate something like that in assembler, you need to do this step by step by, yeah, for example, you could move 3 to RAX, move 2 to RBX, add RBX to RAX. So now RAX contains 3 plus 2. And then you move 4 to RBX and then multiply into RAX. So you can see this is much harder, but yeah, I said assembler is relatively difficult, but yeah, you can still do it. I think it's still doable, and yeah, you just have to think on this low level of moving stuff between the registers and doing calculations inside the registers. Okay, that's really the fundamental thing that you need to keep in mind. And so let's jump right into writing some assembler code. Create a new text file, test.s. Open it with Kate. So in assembler you have these so-called sections. They start with a period sign and then some name. And you can consult manuals about what sections you usually should have. And yeah, the one that you basically always see is this .text section. So this is where your code lives, okay? And you can also have a section .data for something like global variables. But yeah, good. You definitely need this text section, and in here you would have a label underscore start, and labels end with a colon. So yeah, a label is basically just a point, a named point in your code. so that you can refer to that in other places of your code. And yeah, like for example, a function name could be a label, and then calling that function would use that name instead of the actual address. Okay, now for something really simple, I will just move the value 0 into the register RDI, and the value 60 to RAX. Okay, why do I do that? When you're programming in other languages, you typically get some kind of a standard library that gives you access to a lot of things like opening files and allocating dynamic memory and opening network connections and stuff like that. Yeah, assembler doesn't give you these things, and if you want these things, yeah, I mean, other programming languages hide this behind function calls, but when you look at how these things work in the background, yeah, assembler itself just cannot do these things because, I mean, for example, accessing a file. You cannot access a file because you cannot talk to the hard drive. Because if you could talk to the hard drive, then you could access files that you are not allowed to access. So, so what happens is that you cannot directly access files or do all these things. You have to talk to the operating system and tell it to do these things for you, and then the operating system can look at your access rights and stuff and decide, hey, wait a minute, you are not allowed to access etc password. And that works by yeah, writing the thing you want to do into the registers and then calling an instruction called this call. Internally, that's an interrupt, but forget that I said that. Yeah, and this is how you do a lot of these system things, like, for example, exiting your program. I'm telling the operating system what I want to do through the value that I've stored in RAX. And yeah, the value 60 just means I want to end the program. And yeah, the value in RDI is the return code. Okay, so this means that I want to exit with return code 0. Okay, that was quite simple, I think. And yeah, like this, I don't think we would be able to start this because the linker wouldn't see this symbol here. And yeah, the linker needs to see that symbol, so we need to put it into the global symbol table. Okay, like this. This tells the assembler to make this symbol visible to the linker. Okay. Now, okay, here is my test.s, and yeah, now I can just assemble it using the GNU Assembler AS. I set the output file to test.o, and the input file is test.s. Oops. Okay. Now I have this test.o, and yeah, this is just an object file, not yet something that we can execute. To be able to execute it, we also need to link it, and we can link that using the linker ld, output file test and input file test.o. Okay, now I have this test here, and yeah, by the color you already see that this is an executable file, so now I can say test, and yeah, the program just ends, you know, it doesn't do anything, it just exits. So it doesn't do anything here, but we can now look for $?, which is the return value of the last executed program. Okay, so this being 0 means that, yeah, at this point we've received this 0 here from the program. We could also set this to 1 and redo the whole thing. And now we have a 1 here. Okay. Now this label _start, that's the default name for the starting point of your assembler program. You're apparently not really supposed to change it, but if you really want to, you can change it. Like, let's rename this to foo. And then, strangely enough, this is an option for the linker. So with -e, you can change the entry point to foo, and now it still works. But as I said, _start is kind of the default and the standard, and you might get in trouble if you change that, so I would not advise you to do that. Okay, now let's maybe have a look at this test.o. I will open it with Octata, which is a hex editor. And yeah, up here you already see foo, so this seems to be the something like the symbol table of the file. Yeah, here's our 48C7. So 48 is the prefix for 64-bit instructions, and C7 is a move instruction. So yeah, 3C, let's see. So 3C is in hexadecimal is 60 in decimals, so this is our value 60 here that we are moving into RAX. And yeah, this C0 means that it's moved to RAX. And C7 here means I'm moving to RDI, because in RDI I'm storing a 1, you know, this one here, and this 0F05, that's the syscall. So yeah, these are really the these x86-64 commands that, or instructions, that you would also find in something like a list of instruction sets for your assembly. So yeah, let's talk a bit about more things you can do. So maybe we don't want our program to only quit. I don't know, let's do some calculations, like we are moving 1 to RDI, and let's add a 1 to RDI. I don't know if that will work. Yeah, so yeah, now it shows a 2 because we've moved 1 into it, and then we added another 1 onto that 1. Okay, we could also say subtract, and now we get a 0. Okay, so now let's talk about how you can change the program flow. You know, because right now we just start somewhere, we get an instruction, next instruction, next instruction, next instruction, and then we're done. But yeah, when you're programming, you're using loops and if then else and other things. So let's talk about stuff like that. So a very important thing that you need to do such things is the jump. And the jump is yeah, the same thing as a go-to in higher programming languages like C and C++ and other ones. So you need to create some label, and then you can jump to that label. Okay, so I don't know, let's move 1 to RDI, then sub 1 from RDI, but we before sub 1 RDI we jump to foo. Let's see what that does. Okay, we get a 1, and I mean we've set it to 1 here, and yeah, we've subtracted 1 from it, but we didn't actually subtract it because this jump here changes the instruction pointer. So after the jump, this isn't the next instruction anymore, because the jump sets the instruction pointer to the label here. So after the jump, the next instruction is this here, and yeah, here we set we do the system call 60. So yeah, so we've bypassed this sub here. Just jumping around wouldn't be very useful, except if you would do something like jump foo after the foo. That would be something like in a higher language, something like a while true. Okay, but yeah, normally in most cases you wouldn't need an unconditional jump, because yeah, for a while loop, for example, you always need to test if your loop condition is still true, and you only do the jump if it's still true, right? So when you think of if then else or loops, they have some condition associated with them, right? So you need to be able to test something, like maybe you are doing something while some value is larger than 0, right? Then you need to check, is that value larger than 0? If it is, you execute the code, otherwise you jump behind the code, right? So I don't know, let's do something like I will just move some value, let's say 7 to RBX. Okay, and then I want to do a loop in which I iteratively decrease RBX. So sub 1 from RBX. Okay, and then after that jump to the loop. Okay. So this sets RBX to 7, and inside the loop it decreases the value by 1 and then jumps back to the loop. So so we are doing something like in C, something like b equals 7, and after that, while we don't have a condition yet, so this is still while true, b minus minus, but that would of course not be a good thing, because this doesn't stop, you know, it will just continue decreasing b forever, and yeah, that's possibly not what we want to do. So at some point we need to test something. So, and I think in the direction of while b larger than 0. Okay. So how do we test this now? In assembler we have a command cmp for compare, and yeah, now I can pass two values here like 0 and RBX. The CMP stores the result of what it has done inside the flags register of the CPU, and yeah, we then have different instructions for different results that you can have from the CMP. So we can now have conditional jumps. You know, this jump down here is an unconditional jump, and here we can have a conditional jump if less or equal to end of loop. Okay. So here we check if RBX is still larger or equal. And yeah, let's move RBX to RDI so that we can see the final value that it had. And yeah, it ends at 0. That makes sense, you know, while it's greater than 0, it gets decreased, and once it reaches 0, this jump here is executed, and then we finish with the final value of RBX as a return code. And yeah, we are counting down from 7 and stopping at the first time we are not larger than 0 anymore. Of course, this happens when we reach 0. So yeah, that makes sense why we get 0 now. Yeah, this is how you would do a while loop. Importantly, you do this loop jump here unconditionally, because you do this test before you go into the block, right? Let's talk about an if then else. Yeah, so something like if, I don't know, b equals 0, c equals 1, else c equals 2. I don't know, just some random stuff here I'm doing. So we would again compare bx to 0. And yeah, if that is equal, so jump if equal to the then case, so if this condition is true, and if the flags tell us that they have been equal, then we go to the then case. And yeah, behind that we can do an unconditional jump to the else case, because this code will not be executed if the condition was true, you know, then we are here. And yeah, I don't know, let's move $1 to RCX, and in the else case move $2 to RCX. Okay, now at the end of the then case, we cannot, of course, we cannot allow it to keep running, because then it will run into the else case and also execute this code. So here we need to jump past the else case. So if then else end, okay, so yeah, I think this makes sense. And then let's use RCX as a return value, so that we can see the value of RCX. Okay, so inside this loop, again, B gets counted down to 0, so this should tell us that 0 and RBX are equal, so we should go into the then case, set RCX to 1, then jump past this one here, and exit with the value of RCX, so 1 as the return code. And yeah, 1 is indeed the return code. So so yeah, this shows you how you can do some high-level things like a while loop and an if then else in assembler. Okay, now let's talk a bit about input and output, because so far we've only generated output here by yeah, using something as a return value, and then here printing that return value outside of the program. So the program itself doesn't do any input and output so far. Okay, writing to standard out works like this. You have another syscall, so you're talking to the operating system again, and yeah, the code of the syscall for writing is 1. Okay, then you need to tell the operating system where you want to write something, and you do that with a file handle. Now you could get a file handle by opening a file, but yeah, you probably know that in Unix systems everything is a file, including standard out. So so we don't need to actively open standard out. We can just say we can just set RDI to 1. So RDI gets the file handle, and setting it to 1 means we are writing to standard out, okay? So you always have this file handle 1. You can write to it without actively opening something. Now, yeah, this system call needs another information. It needs to know what it's supposed to write. So you need to set the RSI register to a pointer to some string in your in the RAM. And yeah, we can pass just a label here. And yeah, that label can be down here. So .ASCII means you can put prefixes in front of stuff like .ASCII for text, and there's dword or byte. That's kind of like the variable declarations in C++ or something. Now, one thing that I find somewhat annoying is that you also need to tell the system call the length of the string that it is supposed to write. So, but it makes sense, you know. It from the perspective of the operating system. This \n, or maybe something like the C string termination with \0, that doesn't have a meaning for the operating system, you know. So it wouldn't stop printing there by itself. So so from the operating system's perspective, there is just no reason where it should end. So we need to tell it where to end. So how many characters do we have? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Okay, so we need to move 14 to the register RDX. I mean, of course, we could write something that counts the characters until a \0, but that would be a bit much. So I'll just hard code this 14 here. Okay, and yeah, look at that. We've gotten hello world. Why is it saying 73? Yeah, that's probably some return code from the operating system, so that it might have returned through this RCX register. So yeah, I'll just say $0 for exit code 0. Okay, this is how you can do some output. And for reading something, it works very similar. So instead of setting this to 1, you set it to 0. So this call 0 is read. And you need to set RDI also to 0 because file handle 0 is standard in. Okay. Then you need to give some pointer to a buffer where the operating system can store the stuff that the user has entered. And yeah, I will just use this same buffer here. And yeah, you also need to give it the length of the buffer. Okay, let's replace this message with a buffer. So we read into the buffer and yeah, then we print that buffer, okay? So we first read something and then we print that, whatever it is. Yeah. Okay, now it's waiting for my input. Hi there. Okay, now it's printed 0. That 0 probably comes from here, but okay. Yeah, that was the problem. Since this buffer was in the text section, I wasn't allowed to write to it, so I had to move it to the data section so that I can write to it. But I need to warn you, this is quite fragile, because if you input more than this buffer can take, then yeah, only the part that the buffer can take is stripped away from your input, and the rest stays inside the buffer of your console. And yeah, if you end your program, then that will go to the next thing that you're running. And so if you're returning to bash, you could do something like this. So I've started test here. Okay, I'll input 14 characters and just a few more for safety. Okay, and behind that I will put echo test, and yeah, this is the output of the program. Now we've returned to the bash. The bash has taken this echo test and executed it. So if you're not careful with your buffers, then you might have a code injection vulnerability in your program, right? Because I mean, imagine this is running on some web server, and some user is allowed to input something, and yeah, he just needs to input more than he's allowed to then pass on some commands to the surrounding execution environment. You know, that might be an injection vulnerability. So so just be careful with your buffers. Okay. Okay. One very important topic when you are programming assembler is the stack. In other programming languages you also have stacks. For example, in C++, you would have a class that allows you to allocate a stack, and then you can work with that. But in assembler you have a so-called stack pointer, which is just a pointer somewhere into the RAM, and then you have the instructions push and pop. Okay, and yeah, when you push something, for example, you can push constant numbers, you can push register content, like let's say push $0, then you put that on the top of the stack, that value, and the stack pointer is decreased by 1. And if you push another thing, then it goes there, let's say 1, and the stack pointer goes down further. Okay. So yeah, pushing things means you fill data into this, and popping is the opposite. So you could say, for example, pop RAX, and then this moves the stack pointer back, and it is copied into the target that you put in here. So there was a 1, I pop RAX, so this 1 goes into the A register. Now this doesn't sound very spectacular, but this is really a very important thing that you see a lot in assembler programming, because when you have some temporary data, you wouldn't want to define a variable for that, for example. And yeah, the stack is also very tightly connected to things like function calls in high-level programming languages. When you call a function in that programming language, then the generated code will contain some pushs and pops, or they might modify the stack pointer directly, but that's basically the same thing. Okay, and yeah, the stack is in high-level programming languages. The stack is extensively used for local variables of the scopes that you call. Okay, you call a function, then the local data of that function is put on the stack. Okay, and yeah, when you exit the function, it's taken off the stack, and yeah, even the instruction pointer, so the pointer that says where in my code am I currently, you can even push that and pop that, but for that there are two specific instructions. The call instruction, where you can say I want to call whatever. Typically you would have a label here, which refers to the code of a function that you're calling, and then you have a return. That's the opposite instruction of a call. And what these things do is call pushes the instruction pointer. Okay, let's say if this is line 1, for example, then you would push a 1. And then the instruction pointer is changed to whatever you have here as parameter of the call. Okay, so if you have some function, you say call function, then the instruction pointer is now down here. And yes, in this function you would typically do something, and then you have the return instruction somewhere in there. And what that does is this pops the instruction pointer. So so I've been executing this function. Now I hit this return, and this pops the instruction pointer of the stack. So now I'm here at this instruction that I've been at before, and now I'll continue after that. Okay, so this is how you can in assembler do something like a function call, right? Because you are here, then you execute this stuff instead, and then you go back to where you were before. Okay, so let's see some of that in action. I will first make a backup of this test.s. Yeah, let's throw out this loop and this if then else. out this reading here. I will only comment out the writing because I will use it later for the example of call and return. Okay. Now let's just push something to the stack. Let's say 2. And a 4 and an 8, for example. Okay. And yeah, instead of setting RDI to 0 explicitly, I will say pop RDI instead. Okay, so first we push the 2, then the 4, and then the 8. Okay, so the 8 is the top element, so if I then pop into RDI, then this 8 should end up in RDI, so that should be our return code then. Yeah, there you see 8 has been the return code, which makes sense. As I said, this was the top element of the stack, and yeah, when I pop the top element of the stack into RDI, yeah, then that's the return code. But yeah, let's do it just twice. So yeah, I pop 8 into the RDI register first, but then I immediately overwrite it with 4 by popping the next value from the stack into RDI. So if I do this now, then the return code should be 4, and yeah, the return code is 4. Okay, so that's the stack, and now let's talk about call and return. So yeah, I just give some name to this output that I'm doing here. Okay, and I will also make a label for the end of the output, because yeah, we need to make sure that we don't accidentally run into this code, right? If we start here and we don't prevent it, then this code here will just accidentally be executed, and if we put a return at the end here, yeah, that would be disastrous. So that this, I don't even know what would happen. It probably would crash. But yeah, I will just jump to output end here to yeah, to just skip this function here and make sure that we don't accidentally run into it. Okay. Good. And yeah, over here I will call output. Okay, so what I'm doing now is I'm jumping behind this output function. So this is now kind of like a function. And yeah, here I call that function. This function then displays hello world and returns. So then I keep running down here, and yeah, this will then exit the program. So this should now yeah, write hello world, and then So let's run this, and we get hello world and a 0. Okay, but I want to point one thing out. We call this output here, and this function overrides RDX. Okay, so I mean, it needs that for this syscall, but yeah, if we had set RDX outside to something and then yeah, after this call, this 5 would be gone. So yeah, if so this isn't really exactly like a function call, because it can have side effects on your registers, and yeah, you might want to write something like a macro push all, where you would push RAX, push RDI, and yeah, all the registers, and another macro for pop all, which be careful in here. Of course, these things need to be popped in the opposite order, because yeah, if you push RAX before RDI, then RAX is below RDI, and then you need to push, and you need to pop RDI before RAX. Yeah, because the old value of RDI is then above RAX when you've pushed it after RAX, right? Okay, and then you might do something like push all and pop all around such calls, so that this protects your registers. Okay, so yeah, I think that's enough for today. If you like this video, like it, share it, subscribe, and see you next time.